In this video, we're going to finish our section on limits and continuity by doing example 3.2.3 and a quick discussion of continuity. So the example here asks us to show that the limit as xy goes to 0, 0 of xy over x squared plus y squared does not exist. In the last example, we had found two paths, one along the x-axis, one along the y-axis, that gave different values. So we'll try those two paths again. So let's go along x equals 0. If we go along x equals 0, that's the y-axis. That's the same thing as our limit is as y goes to 0. And if I plug in x equals 0, that's 0 times y over 0 squared plus y squared, which is the limit as y goes to 0 of 0 over y squared, which is the limit as y goes to 0 of 0, which is just 0. If we go along the x-axis, so along y equals 0, then our limit becomes the limit as x goes to 0 of x times 0 over x squared plus 0 squared, which is the limit as x goes to 0 of 0 over x squared. Simplify. The limit as x goes to 0 of 0 is 0. So those two values gave, or those two approaches gave me the same value. Can I conclude? Can I conclude, therefore, that the limit exists? No. That is two out of infinitely many different ways. Can I check infinitely many different ways? No, I cannot. There might be a way where the limit does not exist, and in fact, there is. We just have to be a little bit more creative to find it. If we look here at the powers on the bottom are squares. The effective power, right, there's x to the first power, y to the first power is 1, and so the effective power in the numerator is also a square. If I go along the path where y is equal to x, that is also a path towards the origin. And let's have a quick look. The last time we went along x equals 0, that's the y-axis. We went along y equals 0, that's the x-axis. Now we are going to approach along the path y is equal to x, which is the diagonal line through the origin. Y is equal to x. We can approach the origin along that line. Why not? If we approach the origin along that line, well, then the limit becomes either the limit as x goes to 0 or y equals 0. I can choose which one I want to substitute. If I'm plugging in y is equal to x, I'll take as x goes to 0 and I'll change the y's to x's. So this becomes the limit as x goes to 0 of x times x over x squared plus x times x, which is x squared. This is the limit, therefore, as x goes to 0 of x squared over 2x squared. Simplified, that's the limit as x goes to 0 of 1/2, which is 1/2. So we have the limit along the axes gives 0, but the limit along y equals x gives 1/2, a different value. And so we conclude that since the limit along two different paths gives different values, the limit does not exist. The full limit does not exist. So values the full limit does not exist. Good, so let's take a look at continuity. So as with our study of vector curves, we're not going to spend a whole lot of time talking about continuity of several variables other than to give the definition real quickly and one remark. So a function of two variables is continuous at a point AB if and only if the limit as xy goes to AB of f of xy is equal to f of AB. The limit is equal to the function value, which means that AB must be in the domain, the limit must exist, and must be equal to the function value. So as a quick remark, in Calculus 1, in a function of one variable, intuitively, continuity of a function meant that you could draw the function without picking up your pencil. Obviously, you can't draw a surface without picking up your pencil, but the idea remains the same, that the function graph must be connected. So the idea of continuity being intuitively the property of a function graph being connected remains the same for functions of two variables, and in fact, it remains the same in higher dimensions as well.